what's happening. Yes, it's 9 to 23 students join. Let me go ahead with the session. Yes, in the last class, in the last two classes, we had a discussion on the problem solving and a few problems also we looked into. One is the famous and well-noted problem, that's the water jug problem, and we had a set of production rules and applied those rules to get a solution. After that, we had a discussion on another problem, that is the missionaries problem, missionaries, cannibal, and a boat crossing the river, satisfying the constraints. And the same problem we have looked into using the state space, which looks like a tree, which will have a start node, that's a root node, and which will have a leaf node, that will be the goal state, and you will have the intermediate states. So you should start from the root and find a possible solution path such that you reach the goal state. So you will either have a tree representation or a graph representation. So these are the things we discussed in the last class. And this is the one I've asked you to try. See, I'll just give a brief overview on this. I'll not discuss this in detail. You can try out the solution for this. The problem tell you is, if this is the initial state given, I need to be obtaining this state. So I need to be moving the these points over here, these tiles over here, either up, down, left, right, such that I reach my goal state. So what is this? Let's see, look at this problem. Here it says that it has a 3x3 grid with 8 randomly numbered 1 to 8 tiles arranged on it with one empty cell. So at any point, the adjacent tile can move the empty cell, creating a new empty cell. The tiles are arranged in such that we get the goal state from the start state. So you need to be moving. See, this is not physical playing. Indeed, you might have played at your childhood days, but now that we need to write down a code for this, we need to give a solution for this. This is what artificial intelligence is. Look at this. Suppose if this is the start state, where the digits are, the tiles are arranged this way: 3, 7, 6, 5, 1, 2, 4, blank. This is the empty space, and 8. And we need to reach this goal state. 5, 3, 6, and here 7 blank, 2, 4, 1, 8. So if this is the goal state, how do we reach this? So we need to construct a state space set for this, a complete state space tree for this. So, so what should you take the what is to be taken into consideration? Let us represent the empty space by 0. So we need to consider a 2x2 matrix, that is 3x3 matrix, a 2-dimensional matrix. And what's the initial state? This is the initial state, and these numbers represent the tile numbers. See, look at the same thing: 3, 7, 6 in the first row, next 5, 1, 2 in the second row, and then 4, 0. This is the initial state given, and we need to be obtaining this possible goal state. And so what are the possible directions that you can move? So those directions will be the operators. So you will have the up movement, down movement, left movement, and right movement. So these 4 movements are the operators, such that the blank space gets created. New blank space gets created when you move the tiles. So you should be moving the blank tile. You should be moving, it's as good as moving one of the numbered tile. Okay. So this is a partial tree. Do not consider this as the complete tree. You may draw the complete tree for this. So this is the initial state given: 3, 7, 6, 5, 1, 2, 4, blank, 8. So if this is the initial state given, what are the possible next states? What are possible upcoming states or the next states that can be generated from this? See, this is the blank space. I can move the blank space over. That means I have to move one down. Then, or else I can move this blank space to the left. That means bringing 4 over here. Or I can move the blank space to the, I can create the blank space and to the over here. Then I have to move 8 over here. So moving the blank space, that is creating the blank space, is given by this say direction. See, up I say that means I have moved the blank space up. That means a blank space created in the upward direction. So one has to be moved. This is one possible state. This is one possible state. Suppose if you are in the same state and you wanted to create a blank space over here, then you have to move left. So that is moving 4 over here. This is the next possible state. And no, I would like to go out this state. Then I have to create a blank space. So then I have to move 8 from this position to this one so that the A blank space gets created. Okay, this is how the tree gets created. So from the initial state, you had 3 possible states, and every possible state will have 3 more possible states. Try recalling the cine fans, the Stalin movie. 1 helping 3, and those 3 helping 3 more people, and you will have a bigger tree. It's as good as the state space. చూస్తుంటారు కదా అందరూ చిరంజీవి సినిమా స్టాలిన్ అలాగే అన్నమాట సేమ్ వే వినిపిస్తుంది కదమ్మా
Yes, sir.
yeah see suppose if you have chosen this one, what are the possible directions that you can move? You can move to this position, you can move to this position, you can move to this position. See, one of these 3 positions you can move. So which position? Suppose if it is moving up, see, then 7 should come. If it is moving this side, 5 should come here. If it is moving on this side, 2 should come here. 3 possible states. Again, each of these states will have 3 more states. That's, see, you will have a bigger tree. This is just a 9 grid type, 9 grid box. That is a 3 by 3 matrix. Still, you will have number of possibilities. You will have number of possibilities. So each one having 3 possibilities. So if I further explore this, how many possibilities you will have? See, here 3, here 3, here 3, 9 more. So if I keep on doing this, 3 more over here, 3 more, you will have 9. At the next level, you will have 9, 3, 3, 3, 3 again. So you will have a very, very, very big tree. So what's your ultimate state is, what should you understand from this discussion is, you start with an initial state, construct the state space tree till you obtain, which is going to contain all possible states. All possible. You do not know which move you are going to make. See, we will not be knowing which move you are going to make. But our ultimate goal is to reach the goal state. Ultimate objective is to reach the goal state. So you keep on moving, you keep on generating the complete state space and then apply this as we did it for the Mizunari's problem. As we did it for the Mizunari's problem. That's how we use the state space search. Now the question is, should I consider this path or should I consider this path or should I consider this path? As of now, what are we doing? We are randomly moving with some options. We are not using any heuristic function or a goodness function to choose which path to move. So we are randomly. So that's what we are going to focus in the upcoming session. Okay, that's what it says. The control strategies, and this is very, very important for C. You may say, sir, can't we go with this? Yes, you can go with this, but come out with a proper the justification. Which one is to be followed? Which one is to be followed? Suppose if I go this way, if the goodness function is good, definitely I'll end up with a solution. Suppose if I go with this state, if I do not end up with a solution, it's worth wasting time. It consumes more time. So that is where you apply your control strategies. So this is one of the most important components of from 6. We are generating the production rules or we are generating the state space, but we need to effectively apply those production rules or the state space set. Okay, so it describes the order of, say, this is what control strategy is. This is going to describe the order of application of the rules. So I am at this particular state, which move in this direction, should I move in this direction, should I move in this direction? That will be the rule out here. If it is water jet problem, you have a set of rules. If it is Mizunari's that is using the production rules, you will have all the rules. Which rule is to be applied such that you get an optimal solution? That's important. Generating a solution is good, but generating an optimal solution is effective, is efficient. Okay. And when you apply this control strategy, what happens? You move from you transit. That is, you change from one state to another state. Any queries? So we apply this control strategy, you move from one state to another state. So what is that we have been doing till now? We are going with this process. See, we are going with this one approach to select a rule randomly from the available rules or from the applicable rules. See, of course, you may end up with a solution, but this is not a systematic approach. This is not a systematic approach. We need to be adhering to systematic approaches. So here we'll be going with certain evaluation searches or heuristic search techniques, such as the breadth first, which you might have learned in your data structures, the breadth first search or the depth first search. These we call them as systematic control strategies. Systematic control strategies. And these strategies are exhaustive, uninformed, and blind searches in nature. So if the problem is a simple problem, such as that we are working on the cannibals problem or the water jug problem, then any control strategy can cause emotion. You can apply a random choice. You can go with a random choice, as we have done just now. For the missionaries cannibals problem, we have not followed any strategy. We have blindly applied certain rule such that we reach a solution. But if you would like to really solve real world problems, a larger problem, then definitely this blind strategy will not be, this is random selection will not be a true method. So we need to go with the effective control strategy. That is the role of control strategy. Generating a set of rules or generating a state space is one step, but applying them effectively is the key step. That's the reason we normally combine these two, problem solving and control strategies. So there are two directions in which a search can proceed. What are those two directions? One is forward chaining, the other one is backward chaining. I don't know whether we discussed this in the class or not, but if time permits, I'll tell you this, but I have a brief idea on this. What is forward chaining? As the name's implying, forward chaining, you always start with the initial state and try moving towards the goal state. That's what you mean by forward state. So it begins with the known facts, that is the initial state, and work towards a conclusion, that is the goal state. That's what you mean by this forward chaining. And as I already said, the rules are applied in the form of or expressed in the form of if-then statements. So forward chaining, simple way to remember is forward chaining. You start with the initial state, that is the initial known facts, and move towards obtaining the solution. Whereas backward chaining, this is a reverse process. You start from the goal position. You start with the goal and then try obtaining the facts. That is the initial state. So here it's written, it's a goal-directed strategy, which begins with the goal state and continues working backward, generating more subgoals that must also be satisfied to satisfy main goal. And see, in back strategy, we always say that initial state will contain the known facts. The known facts. So these are the two very important approaches: the forward chaining approach and the backward chaining approach. Okay. See, you apply both any of the approach, maybe the backward approach for backward chaining or the forward chaining. The time consumption is more or less same. That's what the computational efforts in both the strategies is more or less same. The state space will be the same. Forward chaining process. The forward chaining process. So when you consider move from the smallest, hello, move from the smaller set of states is my screen visible, Amma?
Yes, sir.
Thank you. Move from the smaller set of states to the larger set of states and proceed in the direction with the, this is it. This is what the goodnet function is. Lower branching factor. Lower branching factor means the node that has less number of branches. The average number of nodes that can be reached directly from the single node. See, you need to see, just because we have two different approaches, we should not blindly go ahead with some kind of approach. When you apply that approach, it should be effective. Always remember that. We need to be always looking for an optimal one. We need to be always moving from an optimal one. That's what you mean by the control strategy and the two approaches, forward chaining and the backward chaining. The network problem, I am joining. Hope I've joined.
Yes, sir.
Yeah, sorry. Network issues. Thank you, Ma. Now, what about J? J starts from 3. Yes. See, three types of problems. One is the ignorable problem. As the ignorable problem clearly tells, where we ignore the solution steps. See, look at the simple example. If some lemma is proved to prove a theorem, and later on we realize that it is not useful, then we can simply ignore that particular lemma and go with another lemma. That's what you mean by ignorable problems. So if you feel that that particular solution step is not going to give you the right solution, then you can ignore the step. That's what ignorable problems are. Recoverable problems. Suppose if you approach, if you move from a starting position and try reaching the goal state, and you can recoverable means that means you can have reverse process taking place. These are the problems where the solution steps can be undone. See, there are certain steps. A start state to initial state, you will have certain intermediate steps, and those intermediate steps, if necessary, can be undone. Those we call them as recoverable problems. For example, see, you have water jug problem. Suppose if you fill the jug, there is a chance to empty it. Suppose if there is an empty jug, you can fill the jug to its brim. That's what we mean by recoverable problems. If it is irrecoverable, you can understand the meanings of those problems just by the names: ignorable, recoverable, and irrecoverable. Suppose irrecoverable problems means the solution steps cannot be undone. Just like your the chess game. Suppose if we are playing, maybe let's say the two of us are playing the game. If two of you are playing the game, if one of the opponent makes a move, would you allow that candidate to again undo the step? You will not do it. The snake and ladder game, playing cards game. I discard a card. Will you give me a chance to again pick up the same card? No, you will not get. Those we call them as irrecoverable problems. A good example is the chess. I make a move, I have to stick to that step. I cannot undo it. Whereas in this water jet problem, I can undo it. That's how you have to understand. So three types of problems: recoverable, irrecoverable, and ignorable. Few more characteristics. Decomposability of a problem. That means you can divide them into smaller problems, which we normally call them as modularity, which you might have learned in your C language, where you try to divide a large program into smaller programs and call them as functions. Okay? And the role of knowledge. Yes, in order to solve a problem, definitely the knowledge base is important in obtaining the solution. And this knowledge is normally represented in the form of rules and facts. That's production rules. It's nothing but the knowledge. How did you generate those production rules? Applying the knowledge only, you have generated the production rules and you have represented that in that particular format. If statement and then the then statement. That is, the antecedent is satisfied, then the consequent is going to take place. That is, consequent means the action takes place. Okay? And the consistency of knowledge base used in problem solving. This is one more. This is one more important problem. See, if the knowledge base is not consistent, what happens? Suppose if you have one knowledge base at one state and at another state, if there is no coordination between the previous knowledge and the upcoming, the next possible knowledge, then you will not have the right solution. Okay? And if you have inconsistent, this is what please say, if you have inconsistent knowledge, what happens? Definitely you will not end up with a solution. The solution you get is a wrong solution. See, that's what our weather predictions, weather forecasting, how does it take place? I've told you this example previously also, the weather forecasting. How does it happen? Earlier, we used to get messages in our televisions and the news, the weather forecast. Today, it's going to rain, they say. Definitely, it will not rain. That was the forecasting maybe 10 years back. But today, the forecasting accuracy is better than the previous one. The accuracy is, we do not say it's 100%, but definitely it is far better than the previous approach, because they had a rich set of data and they had good analytical algorithms. Definitely, if say there is a chance of raining today, yes, definitely a shower takes place. Okay, that's what you mean the consistency of knowledge. So decomposability of a problem, role of knowledge, and consistency of knowledge. And with respect to the requirements of a solution, any problem, it could be any kind of problem, maybe a simple prime number problem or Armstrong number problem. You have to analyze the problem. You have to analyze the problem and find out whether the solution is absolute or relative. So what do you mean by absolute? We call a solution to be absolute if you have to find exact solution. Water jet problem, any path problem solved in reasonable amount of time. So you can follow any particular path. That's not any production rule can be applied, but definitely the solution should be exact. That is, ultimate goal is to be reached. And whereas if you say relative solution, a solution is relative if you have reasonably good and approximate solution. Approximate solution, traveling salesman problem. This is one relative problem, which depends on the previous state. The best path problem, maybe in your data structures you might have learned, finding out the paths. The Kruskals problem, the Prim's algorithm, where you start from the initial state and reach the, where you try visit all the nodes. And the Warshall's algorithm, where you have a path from one node to every other node. So it normally depends on your Dijkstra's algorithm, single source shortest path. What does it say? It clearly tells you the next state depends on the previous state. So that's what relative is. So computationally harder to compare to any path problem. So all these concepts you might have learned in your in your data structures. Maybe traveling salesman problem, you might learn it in design and analysis of algorithms. But all these problems, we normally call them as relative problems. A definite solution, we call it as absolute problem. See, based on these control strategies, discussion, we have several such techniques, and one such technique is exhaustive searches. These exhaustive searches are systematic. These are systematic. That means a definite procedure is followed in order to choose the next node. Systematic, and this is not informed exhaustive search. All these are uninformed exhaustive searches. And out of these 4 searches that have been listed over here, you might be comfortable with the first two: the breadth first search and depth first search. The breadth first search and the depth first search. Anyhow, I'll discuss this, but I may go with the since you are well aware of this concept which you have learned in data structures. I'll not get into depth of those concepts. I'll discuss those topics, but I'll not get into depth of those topics. I'll quickly go through this because I hope you can understand those concepts. See the breadth first search. How many of you do remember this? The breadth first search. Did you solve this problem in data structures? I do have a very good number today, 59 students. Oh my God, only 10 students are absent. Do you have an idea on what breadth first search is, which you might have learned in the graphs concept, BFS and DFS?
Yes.
Could someone tell me? Just in brief, not in detail. Okay, I'll ask you a simple question. In breadth first search, which data structure is being used? Very good. In depth first search?
Stacks.
Very good. At least one student has responded, and the answer is absolutely correct. So, breadth first search, this is going to go level by level. This is going to go level by level. So, the breadth first search expands all the states one step away from the start state, and then expands all the states 2 steps from start state, and then 3 steps, and so that's what you mean by level by level. You are at the initial state, you go to the next level. Once you explore all the nodes at that particular level, then you go to the next level. Once you explore all the nodes at that level, then you move to the next level. That's how the BFS takes place. So all successor states are examined at the same depth. That means they are at the same level. All successor states, they are examined at the same level. So BFS will normally give you an optimal path or solution. BFS always gives an optimal path or solution. And see the implementation process, whatever you are aware of that you have learned in graphs, the same implementation process can be continued with. Here, the terminology slightly changes. The search is implemented using 2 lists called an open list and a closed list. The open list contains those states that are to be expanded, that means which are not yet visited. And the closed list keeps track of states that are already expanded. Already expanded means already visited. See, in the data searches in my set, I've said a visited set and unvisited set. Here we are using the words as open and closed. Open means the nodes that are not visited or the nodes that are not expanded, which are yet to be expanded. Closed means this list contains all those nodes that have been already visited or expanded. See it clearly. Look at the last one. Open list is maintained as a queue because we go level by level. And just now one of our friends said that BFS normally uses the queues as the data structure for its implementation. And closed list is maintained as a stack. Suppose why are we maintaining a stack or these states are already expanded? So we are pushing them into the stack. So 2 data structures. Open list, we are using the queue, and for closed list, we are using the stack. And look at this algorithm, which is a quite familiar algorithm, which I need not explain. And you are well versed with this. So look at, let me go through these lines, even though you are aware of the input state. That is the start state and the goal states. Because if those two states are known, then only you go ahead with writing down the procedure correctly. What are the variables? Just now we said we require two data structures. What are those two data structures? One is open, which is maintained as a queue, and the other one is closed, which is maintained as a stack. Besides these two data structures, we also require state X, that is the current state of X. What is the followed successors? And then if it is found or not, our solution is found state or not. So when you, what will be the ultimate output? A positive output or a negative output. That is, you have reached the goal state, you have not reached the goal state. See, henceforth, when you write down the algorithms, please follow this approach. See, you might have been used to other kinds of writing down algorithms, but henceforth, you always give this. The first one should be the name of the algorithm that you are going to write. Then you need to provide the necessary input for the algorithm. So specify it as input. What are the variables you are going to use? What is the ultimate output? And then you go with the actual methodology, the actual procedure of the algorithm. So it says that, sir, initialize open with the open list with start. Initialize open list with start, because this is a queue. You need to put start enqueue the start portion into this open list, and the closed list as of now no node has been visited, so that is an empty set. Now, what's the initial state of found? Did you find it? Is start state your goal state? No. So we say found is equal to such the initial state is false. So how long you keep on going? As long as there are nodes available in the open list, that is open queue. So that's the condition you are writing over here. Say while open not equals to empty list and found is equal to false, you keep on repeating the process. You keep on repeating the process. See, once if the solution is found, even though there are values left over, nodes left over in the open list, we are not worried. If both are satisfied, that means if open node is equal to empty, that means it still has nodes to be explored, expanded. And at the same time, the found is not a true. So we need to continue the process. So while open is not equal to empty, because what is open initially containing? The start state. And what is the initial state of false? It is false. Found, it is false. So with this condition being satisfied, we will run through these steps. Remove the first state from the open. What is the first state from the open? As of now, you have only the start state. And that will be your current state, and call it the state X. The state X is for the current state. Put state X in the front of the closed list. See, once it is removed from the open list, which is being maintained as a queue, what does it imply? That node is visited, which is to be now expanded. So that state X is placed in the front of the closed list. That is into the stack, which is maintained as stack. So if the state X is equal to goal, see here you always specify the goal state also. If the state X is equal to goal, and then what do you say? You need to set this found value to true, because initial value of found is false. If state X is equal to true goal, and then found is equal to true. So if this is going to happen, if found is equal to true, what happens? Again, it goes to over here, the loop breaks. Suppose if state X is equal to not equal to goal, then this will not function, and then it's going to go to this else part. In the else part, what should you do? You have removed an element from the open, which is your current state. You have to expand that, explore it, perform expand operation on state X. That means what are the nodes that are available at the next level? What are the nodes available that are available at the next level? So that the nodes that are available at the next level is nothing but the list of nodes, which we normally present in the successors. See, what I mean to say is I have the initial root node. This may have three nodes. This may have three nodes. So just now we have seen this eight puzzle problem. The first state has three nodes. The first state has been removed from the open. Suppose if that itself is the goal state, you will stop there. You need not further proceed. Suppose if that's not the goal state, what are the three possibilities it had? So all those three possibilities will be placed in the successor. So perform expand operation on state X, producing a list of successors. Remove from successors those states, if any, that are in the closed list. Suppose if any of the nodes that are present in the successor state are present in the closed list, do not further explore them. What does it imply? If any node is placed in the closed list, what does it imply? It has been already explored. So you need not further explore them. So remove from successor those states, if any, that are in the closed list. Append SUCC, that is successors, at the end of the open list. Hope you are getting this procedure. A simple procedure which you are already aware of and learned in and implemented in data structures. You are starting with an open list and a closed list. The state X represents the current state of the node. Successor will have what are the nodes at the upcoming level, the next level, and found specifies the state of the problem. So initially open will have the start state and closed list is empty. The initial state of found is false. So you have to run through the statements based on this condition. How long would you run through this? While open and not equals, that means if there are some nodes left over in the open, at least one node, you continue. Open not equals to this, and the state of the found is false, you continue this process. So initially open has one node and the found is false, so the process continues. Remove from the state, remove the first state from the open, and that will be your current state. Okay, once it is your current state, what do you mean by that? You have already visited it. That means you are ready to explore it. So push that into the closed list. Suppose if the start state itself is the goal, set the found to true and end the process. Suppose if this is not true, then perform these steps. So whatever is your current state, just explore it. That means generate all the possible nodes that are available at the next level and place them in the successor state. Suppose in this successor state, if there are any nodes that are already present in this closed list, then remove them from the successor state. All the remaining nodes will be placed in the open list and continue the process. Continue the process. Suppose if state X is equal to goal, what is that we are saying? Found is equal to true. Definitely the loop ends. And if found is equal to true, what does it imply? The solution, you have obtained the solution. If found is not equal to true, even after expanding all these, then the solution is false. Stop the process. So this is what the breadth first search algorithm is. See, why am I stressing on this? You need to understand this and try developing your own problems, your own program for this, based on this algorithm. Okay? The production rules for water jug problem. See, this we have already seen. We have already seen, this is the very first problem we discussed. The same 8 rules have been given over here. See, we are trying to work out that using this. Now see, what is it? This is the state space search. State space search. This is the initial state. Initial state. So I can fill the first jug. That means I apply the first rule. If I apply the first rule, what happens? I will fill the first jug. Look at this, kindly understand this. If you understand this, the BFS would be very clear. This is the state space search tree. So if I apply the first rule, these the arrow marks, these edges are labeled with the protection rule numbers. 50. This is the operator being used. So if I apply the third rule, this is 03. On this, if I apply the rule number 2, what is rule number 2? Emptying the jug. So the next state would be 00. On this, if I apply the rule, which rule number? If I apply the rule 3, what is rule 3? I'll have 3 gallons of water in the second jug. So first jug will have 5 gallons of water, the second jug will have 3 gallons of water. If I apply rule number 8, what is rule number 8 say? Rule number 8, you are pouring water from 5-gallon jug to 3-gallon jug. So if you say you have 50, if you pour the water from 5-gallon jug to 3-gallon jug, you will be left with 2 gallons of water in the first jug and 3 gallons of water in the next jug. Is that clear? Similarly, if you are trying to explore this, see if you see breadth first, you start from this will be initially placed in the open list. If this is your goal state, yes, you will definitely end up with your solution. Or else this has 2 possible states and these are your successors. These are your successors. And this 0, 0 will be placed in the closed list. Now is 50 or 03 available in the closed list? They are not. So these successors will now be added to your open state. That's how you apply the BFS algorithm. Suppose if I expand this, which rule? If I apply rule number 1, for first jug will have 5 and second jug will have 3. If I apply rule number 4, I'm going to empty this second jug, then I'll have 0, 0. If I apply rule number 5, I'll be pouring this water from the first jug to second jug to the first jug. Then I'll have 3 gallons of water in the first jug and 0 gallons of water in the second jug. So based on this, this is how this is one level. So once these two are explored, see I have the open list containing of 2 nodes and the found state is still false. Then I'll go with the expansion of this. Will this give me a solution? No, it will not give me the, so I need not further explore this. Will this give me a solution? Yes, I need to. So I have to further go. At this particular step, I cannot say whether it's going to give me a solution or not. That means whether I can apply a proper rule on that or not out of the available 8 rules. So this kind of generation is nothing but your state space. On this state space, you can apply your BFS, and this state space has been generated using BFS. That's the interesting point over here. The set tree has been generated using BFS. That means you have been exploring the nodes level by level. Once these nodes are explored, then only you move to the next level. Level by level expansion takes place. So this tree itself is generated using the level expansion. Level by level expansion. See here, this is what your goal state is. So what will be your path? I have to come this way, I have to come this way, go this way, go this way, go this way, go this way. What does it imply? Rule number 1 is to be applied, then rule number 8 is to be applied, then rule number 4 is to be applied, rule number 6 is to be applied, rule number 1 is to be applied, and rule number 8 is to be applied. Would you like to say that this is the only solution available? Definitely the answer is no. This is not the only solution available. This is one of the solutions available. This is one of the solutions available. So this tree has been, kindly understand, this tree has been constructed or generated using the BFS approach, using the breadth first search approach for the water jug problem. See, here you need to understand how the nodes are being expanded, explored. Level by level, it's moving ahead. That's what is to be understood over here. See the solution path, as I said, it started with 0, 0, then went to 5, 0, then 2, 3, then 2, 0, then 0, 2, then 5, 2, and finally 4, 3. That's what the solution path is. And this path information, where will you find this path information? Every time a node is being explored, that's being passed into the closed list. See, the path information can be obtained by modifying the closed list in the algorithm by putting a pointer back to its parent. It's maintaining it as a linked list. But as far as memory efficiency is considered, this is not memory efficient because we are going to explore all the nodes at the respective level. As partially developed tree is to be kept in the memory. See this part, we don't see whether this is necessary or not, we need to store it in the memory. Whether this is necessary or not, we need to keep it in the memory. So this is not memory effective, memory efficient. But still it's going to give you a optimal solution. That's important already. Even though it's not memory efficient, it still yields an optimal solution. This is how the breadth first search generation of tree can take place and the solution path can be found. I'll not go ahead with this. I'll go ahead with the remaining 3 such techniques in the next class. It's 9:47. Any doubts, please? Any doubts, Amma? See, these techniques, yeah. These techniques, you are already familiar, the first 2 techniques, the breadth first search and the depth first search. But you need to apply that to our artificial intelligence. See, moreover, the algorithm does not change. How we apply, how we generate the state space tree using a BFS, how do you generate the tree using DFS? That's important, and accordingly apply the algorithm for it. And what are the data structures that we are considering while working on it? That's important for us. Okay. Amma, please post the attendance, Amma. But today we had, see, almost 61 or 62 students are present. Indeed, a very good. But my sincere advice to everyone, please don't miss the continuity. If you happen to miss the continuity, you will not understand that. Whatever I teach you in the previous class is a continuation for the next class. If you happen to miss the previous class, you will not have the continuity, and as a result, you will not understand the concept. And you may simply say that this sir is not teaching well, as good as that, because you have that weapon with you. So please see that you are present for all the sessions, and still if you have a problem in understanding the concepts or implementing the concepts, see the first assignment that I've given you on what is that tic-tac-toe problem, if I remember. When I've seen the state morning, only 39 students submitted. 30 students did not submit. The due date is over. See, this is only for your goodness, preparing you for the campus interviews. This artificial intelligence will play a very critical for you in your recruitment phase. If you can develop programs for whatever I'm asking you, this will definitely help you in securing a job of your choice. I can guarantee you, if you are good at applying Python for artificial intelligence, you will be assured with a job. Rest is left to you. Whether to do it or not is left to you. See, getting marks for sessionals and all this is a secondary part. Anyhow, you have to do it. I will be giving some marks. That's a different story. But your career goal is important. Please go ahead with that positive mindset and work on whatever assignments that I provide you well within the deadline. Because once you get into the industry, there will be targets, always targets. You will be given deadlines. You need to submit your project work before the deadline. And just as you do it for our assignments, you cannot, the same process cannot be repeated. Okay, thank you, and meet you in the next class on Thursday. You can leave.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.